Kannan Gopalakrishnan. He was working as a senior architect at Engineering Design Research Centre, L&T Construction, India's largest construction company. He's also worked on projects ranging from institutional buildings to international airports, apartment complexes to aircraft hangars. He's also attended 3 international conferences and 2 national conferences, and has also presented technical papers at the Jawaharlal Nehru University, Delhi, and the MSRIT, Bangalore. He's also won the national championship at Archaman at the India's largest architecture quiz. Sir Kannan Gopalakrishnan currently runs a design firm, Habitat Design Studio, and he is also a visiting faculty at the renowned architecture schools in Tamil Nadu.
Welcome back to another episode in UGC lecture series. This is lecture 6 and we will be covering a portion of unit 2 which will be dealing with history of structural design in the post-industrial period. The previous episode we remember seeing large span structures, introduction, different types of classification, the ways and means in which we can do large span structures. In this episode we will be looking at continuation of different other long span structures and various different types of classification of long span structures. We will also be looking at pneumatic structures in detail. So, let us get into long span structures. We saw that long span structures can be classified into various different types, and we also saw the different forms and different sizes and different shapes, different materials that different kinds of long span structures took. We also saw the bare beginnings from the early cathedrals and churches which were built during the Renaissance and the Gothic period. From there till today we have so many long span structures, such massive structures based on our requirement, based on our functional requirement, based on our congregational requirement, and based on the size and volume of things that we operate today. We have so many long span structures today. Now we are going to look at long span structures and we are going to divide them into different other types, but before that we should first understand the different kinds of loading which acts on a long span structure. The first load anyway is always in any structure is the dead load of the structure itself, because any structure is made up of some or other material. When some or other material has a certain weight in itself, the weight of the material also acts as a weight of the structure. Usually dead loads are the ones which are making up the most of the loads in many structures. Similarly, long span structures also have dead load as a major component. Next, of course, is the live load. Live load is the sum of all loads which can be moved into and moved along in the building. For example, people, furniture, other arrangement like partitions, all the electrical equipment, mechanical equipment, the service equipment that we put onto the building which can be moved from one place to another at some point of time are all live loads. Live loads also come up to a good amount of number when you take loading action into consideration. Next load is the wind load. If there is a structure and the dead weight of the structure and the live weight of the structure which are there inside the structure are the only loads which act on the structure. There are other loads which act from the environment, from the outside. If there is a wind, especially in tall buildings and high rise buildings, the wind load is something which should be calculated very, very carefully, because wind has the power to uproot buildings. We have also seen that during massive hurricanes and massive cyclones, trees and other buildings also get damaged. That is because of the wind load. All buildings that we see around are all designed for wind load, so that the wind load can be taken into consideration. The buildings are either designed so that the wind can be gone around the building, the wind will be taken around the building, or the buildings are strong enough to withstand the pressure of the wind itself. There are other types of loads which also act on the building. There are some loads which are created due to the stresses by temperature differences. For example, we have a concept of thermal expansion. Any material given heat will expand, and any material when it is cooled, it will contract. So, this difference in temperature creates some stresses within the material, stresses within the element. So, this also has some loading action. There are other sources which are created in the form of disruption, including ground movement, vibration, deformation, earthquakes, any other forms of natural disasters. All these loads are calculated into a large span structure to make it efficient and to make it usable in a long period of time. If we are to divide long span structures into different systems, we have 4 major categories, being the major categories of systems: vector active systems, section active systems, and surface active systems. We look at each of these systems in detail. First up, we have form active systems. Form active systems are systems of flexible, non-rigid matter in which the redirection of forces is effected by a particular form, design, and characteristics form stabilization. In simpler terms, any form, any element will have a certain form, and the forms create certain strength to the overall structure, in which the structure itself can be flexible. It could be non-rigid, in which the forces can be redirected or changed from one direction to another direction by a particular form of design. For example, tent structures. In a tent, we saw a mast and then we saw the cloth which forms the element. So, these are flexible, non-rigid. At the same time, the overall structure is stable only because of the form of the elements which are in action. Form active systems are again divided into many types of structures: cable structures, tent structures, pneumatic structures, arch structures. Let us look at some examples of each of these structures. These are cable structures, and the picture on the top is a parallel cable structure, and these are structures that are formed by an arch action. There is an arch, and then the arch is expanded, contracted, made it larger, made smaller, and arranged in different sizes, different locations, and voila, the structure is formed by a series of arches. These are tented structures, masted structures, multiple tent structures. These are pneumatic structures. Pneumatic structures are structures in which air is controlled inside the indoor of the element, and we will be looking at pneumatic structures in detail at the end of this same episode. The next system that we are going to look at is vector active systems. Vector active systems are these that have short, solid, straight, linear members in which the redirection of forces is effected by vector partition, that is, by multi-directional splitting of single force simply to compression or tension elements. And these are elements where the overall structure is divided into multiple short, solid, straight elements. As in, if there is a big element, the element itself is made up of short, small, little elements, and in which the forces are completely redirected within the whole system in such a way that the forces are split into different members. There are some members which will take tension and there are some members which will take compression. For example, trusses. Trusses are the best example for vector active systems. We have different kinds of trusses. There are flat trusses, curved trusses, space frames, space trusses. We are looking at some of the pictures of trusses. These are flat trusses, for example. There are different types of flat trusses. The trusses which have a triangle in which the apex is on top and the triangle in which the apex is at bottom. And there are curved trusses where we can have a curvilinear roof on top. Even though these are straight elements which are different straight elements, rigid struts which form the overall curve, but then if you look at the overall form, it looks like an arch, like a curve. So that is why we call it curved trusses, even though none of these little elements are curved. All of these elements are straight lines. Next type of system is section active system. These are again systems of rigid, solid, linear elements in which redirection of forces is clearly effected by simple mobilization of sectional forces. For example, we have slabs, beams and other frame structures where they are not small items, they are rigid solid items, but not to mention not small like a truss. They are not small elements, they are pretty huge. Column can be as small as a 3-meter column, or it could be something massive like a 12-15-meter column or even more. Similarly, beams can be 3 or 4 meter beams, or it can even be a 12-meter, 15-meter beams, depending upon the size, depending upon the loading pattern. Here, the redirection of forces is affected by mobilization of sectional forces. The beam shall have a section, and the section itself will carry both compressive and tensile loads. These are some of the section active systems. There are some beams, there are some slabs, lattice beams, different sectional beams, single section, dual section, slabs. These are sections of a section active system wherein you can see the load action clearly that is being transferred from a slab to a beam to the next element below. The last and the final system which we are going to look today is surface active systems. These are flexible or rigid elements, planes, that are able to resist tension, compression or shear, in which the redirection of forces is affected by mobilization of sectional forces. For example, we have folded structures. We looked at folded plates in the previous episode, where a plane of paper is not able to take up any load if it is a plane of paper. At the same time, a plane of paper, when it was folded multiple times, it was able to take immensely huge load which we did not expect it to take. Such is the effect of a surface active system. These are some of the surface active systems. These again are some other examples of surface active systems. Now let's look at pneumatic structures in details. Pneumatic structures are a type of form active systems. If we remember our four main classification, form active systems were the first of the four, and we saw pneumatic structures as one of the examples of form active systems. If you look at the etymology of the word pneumatic structures, the word pneumatic is derived from the Greek word pneuma, meaning breath of air. Thus, these are the structures which are supported clearly by air. These structures have been used by mankind for thousands of years in the building technology, but it was introduced to us in the construction field only about 40-45 years ago. Now let us look at the fundamentals and the principles of pneumatic structures, and let's see how it works. Its principle is simple. It uses a relatively thin membrane supported by a pressure difference. There is air outside the membrane, there is air inside the membrane, and there is a pressure difference between these two membranes, and the pressure difference is the one which keeps the membrane afloat. So through increasing the air pressure inside, there are two real advantages which we get. The dead weight of the space is clearly balanced, because the weight of the substance is not directly taken by the load itself, but because of the difference in air pressure, the dead weight is clearly balanced. The membrane is stressed to the point where it cannot be indented by asymmetrical loading. It's air, it's a fluidic substance. It can go take up any space which is there. It takes the shape of the structure in which it is holding. The membrane is stressed in such a way that there is no one point where the loading can become more or loading can become less, and thereby disrupting the whole structural system. That cannot happen in a pneumatic system usually. In this picture, you see that there is this membrane which is being stretched on both sides, and from the internal side, there is an air pressure which acts on the surface, throughout the surface, so that the membrane's size and the form and the shape is retained. On top, there are wind loads, there are snow loads, and of course there is a gravitational load which is happening, and there are some foundation reactions which counteract the tension forces on the bottom. So thereby the overall structure is retained in a perfect intact condition. Here again, pneumatic structures are classified into two major types. One is the air supported systems, and another is where air inflated systems. These are the pictures of air supported systems on the right, on the left, and there is an air inflated system on the right. Let's look at technically what the difference between air supported system and air inflated system. If you look at the slide, it says here that it consists of a single membrane supported by a small internal pressure difference. the internal volume of a building air is consequentially at a pressure higher than atmospheric pressure. For example, it consists of a single membrane. There is a small pressure difference between the external air and the internal air. The internal volume of the air is at a higher pressure than the atmospheric pressure, because there is a higher pressure in the inside, so that there is an equal pressure which is applied on the membrane in such a way that the membrane is kept afloat. Whereas in an air inflated structure, it says here that it is supported by pressurized air contained within inflated building element. The internal volume of building air remains at atmosphere pressure. Here it is supported by pressurized air contained within the inflated building element. So which means there is no single element, there are two elements, and there is a pressurized air which is happening inside the thing. The internal air is at the same pressure as the atmospheric air. If you look at the pressure diagram, you see here there is one element from where there is an equal internal pressure acting from the inside, and there are wind loads and snow loads and gravitational loads acting on the outside. The internal air pressure is higher than the external air pressure, thereby maintaining the rigidity of the form. Here in an air inflated structure, what happens is there are two membranes and there are internal pressures between the two membranes in such a way that the whole system is kept afloat because of this internal pressure, and the air inside and the air outside is of the same pressure. Now let us look at the different components in a pneumatic structure. There are four main components which we need to understand about. The first component is the envelope. The envelope is a skin of the overall pneumatic structure, and it could be made of practically any material that can be stretched. The usual materials are made up of polyurethane, polythene, and the other synthetic rubber and any other usual pneumatic structure element. And the other thing which we need to understand is about the pumping equipment, where we need to have pumping equipment that constantly keeps when we keep setting up this whole pneumatic structure up, we need a pumping equipment so that we can set up the system in a relatively quicker time. Next up, we need to understand how the air locks act in an entrance door. When you are entering a pneumatic structure, when you are exiting a pneumatic structure, when you open the door, if there is a pressure difference between the internal air and the external air, the moment you open the door, the pressure difference is neutralized. We cannot allow that to happen. So that is why we use an air lock system, where the pressure is remaining the same way even after when a door is opened. So there is an air lock system which is installed at all entrance doors, which acts as a pressure barrier. And next is foundation. Foundation depends upon the longevity of the structure, and it also depends upon the kind of element, kind of material which we use. So next we will be looking at different advantages and usual characteristics of pneumatic structures. From the slide we can see that it is a lightweight structure. It spans a relatively large spans when compared to other structures. When you are talking about lightweight structure, we are talking about extremely lightweight structures, and when you are talking about large span structures, we are talking about very large span structures, because theoretically a pneumatic structure does not have a ceiling limit of span. Theoretically, we are talking about kilometers of span. We are talking about kilometers that range from 30, 36, 40 kilometers range, which can be theoretically done by a pneumatic structure. Then we say that the pneumatic structures are pretty safe when compared to the other structures, because even if there is a failure, structural failure, there are no rigid heavy elements that are going to fall off from the building. We are not going to get trampled by slabs falling on top of us. All the elements, everything is made up of fabric, and hence they are very safe. It is also theft proof. It is also safe from external miscreants, because the moment you use a knife or any sharp element on the surface of the building, what happens, there is a blast of sound which it creates. When the pressured air leaks out, there is a blast which is heard, and everybody is quickly awake, and a theft really cannot happen. Another advantage is we have here is a quick erection and quick dismantling of this structures. Typically, a 1 kilometer square, 1 square kilometer area of pneumatic structure can be dismantled in 6 hours, and it takes only 10 hours to assemble the entire system. The difference of 4 hours is because to put the poles and the pegs right to get the foundation right. So other than that, to dismantle a 1 square kilometer of pneumatic structure, it only takes 6 hours. To assemble a similar structure, it only takes 10 hours. And it is economical when compared to a regular structure, because this has the advantage of the relocatable. A structure that can be used here can be used in some other city tomorrow, and it can be used in some other place day after tomorrow. So which means you don't have to invest a lot of money onto your building. It can be relocated, it can be assembled, it can be dismantled, erected at your will. So that way it is economical. And it also produces a lot of natural light inside. If you see in this corner picture here, we see that there is a lot of natural light that can be brought in inside the building, and the amount of natural light which can be brought in ranges from 50 to 80% depending upon the material of the fabric. Talking about material of the fabric, we will be looking at some of the materials which we can use as a fabric. There are two basic types of materials which can be used here: isotropic materials and anisotropic materials. To tell you simply what isotropic and anisotropic materials are, an isotropic material produces the same elastic, same structural properties on any sides, any axis, whereas an anisotropic material has different properties when you expand it in a different way. A simple example will be fabric where there are only woven fabric where there are only 2 axes of threads, and if you apply force on one particular axis, the fabric tears up exactly in that particular spot. That is because it is anisotropic, it does not tear in any manner. So isotropic materials such as plastic films, fabric such as elastomers, rubber membranes, metal foils, all these elements can be used in pneumatic structures. In anisotropic materials, we have woven fabric, gridded fabric, and synthetic rubber which can be used to get pneumatic structures. Okay, now we have come to the end of this lecture, so we will look at different learning outcomes that we have studied in this lecture so far. We have got a broad understanding further into the realm of long span structures, wherein we tried to classify the long span structures into another ways in terms of systems. We saw 4 different types of systems, and we also saw pneumatic structures in detail. We understood their principles, we understood the different types of 2 types of pneumatic structures. We saw the different components which are used in a pneumatic structure. We saw their advantages. We saw the different materials which can be used to make pneumatic structures. So with these learning outcomes, we should be able to answer some of these questions here. Let's see if you can get it right. What are form active systems? Explain them with sketches. What are vector active systems? What are surface active systems? What are pneumatic structures? Explain their working with relevant sketches. What are the advantages of pneumatic structures? You should be able to answer these questions by having attended this lecture series. And with this, we come to an end of this episode 6. We'll be looking forward to meeting you in the next episodes. We have a lot of case studies, and we have a lot of architects and their works in the next episodes. Thank you.